Welcome back, everybody. So we were in the middle of looking at this, which is a function. We have the set of functions from a set to another set. And then we have this way of saying a value is associated with a value via this function, right? And this is just a visual representation of the function. This is an example of a function where we associate, for example, ETH Zurich with Zurich, EPFL with Lausanne, UCL with London, UZH with Zurich. And we can also write, for example, for this row right here, we can write it down like this in math, right? ETH Zurich is associated with Zurich. And F belongs to the set of functions from universities to cities. I was asked during the break, like, can we have pairs in sets? And the answer is yes, you can absolutely have anything you want in a set. This is exactly the reason why this is so complex, right? You can have a set of anything you'd like, even heterogeneous. You can even put potatoes and universities and whatever you want in a set, in the same set. Okay, so that's the set of universities to cities. This is also related to data. Maybe in a different way. This will become clear when we are in database design theory in a few weeks, that will have functions like this that go from values to values, right? But at that point, I'm just giving that to you as an example of function. Okay. Then we have, we can relax some constraints. So here there was the constraints that the function associates a value with every element of the set on the left. But it doesn't have to. You can also have the case where you're not mapping every value on the left to something on the right, but you can also omit some of them. And in that case, that's called a map. So that's the computer sciencey way of saying that. It's a map. Can also be called a partial function by mathematicians. I mean, you can have different conventions. In that case, basically, what makes it a bit tough in math is that you have to distinguish between this set here, that is the whole domain of the function, but you have to distinguish with this here, that is kind of the pre-image, right? It's basically only those that have a row starting from them. That's also called the domain of definition of this. So, but for the purpose of the lecture, we just say, okay, this is a map, and it just associates every value from A with 0 or 1 values from B, okay? You also have the possibility that 2 of them go to the same. You also have the possibility that some of them are not associated with anything. So here it's just 0 or 1 arrows that leave. That's called a map, okay? We use the same notation for the maps. You know, it can be seen as incomplete functions, like partial functions. So we have the same notation here. That would be for this arrow right here, that we write it in this way here. And then the notation is similar for the set of maps. It's similar to the set of functions. You just strike the arrow like this. Normally, it should be vertical, the way you strike it. I was totally unable of finding any LaTeX symbol that has this. So I really looked for a long time. I didn't find that. So the closest I could find is this slightly inclined way. But yeah, that's the closest I found. So that's the set of maps from A to B. This is an example of map that says name ETH Zurich, city, Zurich, department, DMath, right? And the arrow from city to Zurich can be denoted as city with this row here associated with Zurich. And that function is a partial function, a map, from the set of strings here to the set of values here. We have a question on Zoom, I think.
Yes. So does it matter that the city Frankfurt is not used?
In which slides? Here?
Yes.
No, it doesn't. That's absolutely fine. Because when you have a function, you don't have any constraints on the fact that every element on the right should be the arrival of an arrow, right? The destination of an arrow. You also don't have any constraint that it has to be unique. Here you have 2 incoming arrows. But if you do want to capture and say, okay, I want Frankfurt, I want every element in B to receive a visit from an arrow, there is a name for that. Do you know what it's called? Surjective, right? Yeah, surjective. So surjective means that every element of B receives a visit. So they have an arrow, they are mapped somewhere. That's surjective. Injective also exists. So injective, let's see. Injective means that you cannot have collisions like that. Injective means that you are not allowed to send two of them to the same. That's called an injective. Surjective means that this is forbidden. And bijective means that it's both ways, right? It has to, you can revert the function. You can invert the function, swap the direction of the arrows, and that's still a function. That's called bijective. Okay? Does it make sense? On Zoom, did I answer your question? Yes, perfect. Thank you. Very good question, because indeed that is something asymmetric, right? The fact that for a function we require every element of A to be associated with something, but not on the right, right? This is indeed asymmetric when you look at functions. Okay, so this is a map, and here we also do not force every value on the left to be associated with something. That's an example of map. This, you might see a link with the relational table in here. Who sees a little bit the link with relational tables here? In fact, you could sense that what's on the left is an attribute, what's on the right is a value. So you probably see it coming, right? This is where it's going. Okay. So we have functions and maps. In fact, we have something even more general than that. It's called a relation. In a relation, we completely relax everything. We even allow for an element on the left to be associated with multiple elements on the right. That's called a relation. Basically, all functions are relations, but not all relations are functions. This is not a function, right? Because orange is associated with 2 values, red is associated with 3 values, so that's not a function, right? If you want a function, you really need to have only one outgoing arrow from every element on the left. So this is a relation. In a relation, so we can call it R, that's a relation. It's a subset of the Cartesian product of A and B. Oh, we have seen that somewhere. Subset of the Cartesian product of A and B. What is that? What is an element of the Cartesian product of A and B? A pair, exactly. This is a pair. So a relation is a set of pairs. What are the pairs? These are all the black lines. Every black line here is a pair, right? So we have basically orange, green, that is a pair, orange, yellow, and so on. So how many pairs do we have? 1, 2, 3, 4, 5, 6, and 7 pairs. Okay, so this is a set of 7 pairs. Now, if you consider the whole Cartesian product, that would be all possible pairs, right? So if you consider all possible pairs from A and B, then you have the whole Cartesian product. What I would like to give you as an intuition is that if you have the whole Cartesian product, in terms of databases, that's totally useless. Because what is the point of a database? The point of a database is to find relationships between things, right? So if you have a relation with all possible relationships in there that can possibly exist, you learn absolutely nothing. There is zero information. The whole point of having data and having information is that you have some pairs in here, but not all of the pairs, right? An example is, imagine you have ETH Zurich associated with Zurich in a relation. That is information. But if you also have ETH Zurich London, ETH Zurich San Francisco, ETH Zurich Beijing, and so on, with every city in the world, then you have absolutely zero information in there. You only have information if it's only associated with cities that are, in fact, in the real world associated with ETH Zurich. For whom is that clear? Right? So this is why a relation is really a subset of the Cartesian product. It's not the whole Cartesian product. It's a subset of the Cartesian product. Okay, so that's called a relation. Now, there is a relationship between functions, maps, and relations. The idea is that all functions are maps, and all maps are relations. Okay. In other terms, and here I'm going to give you a headache, the set of all functions is a subset of the set of all maps, which is a subset of the set of all relations. Right? Who gets a headache with that? You know, you see that this can start getting complex, but you don't have to express it this way. You can just say all functions are maps, all maps are relations. Okay. All right. Now, some mathematicians like to write the same thing like this. They basically have a name for the all possible sets of pairs. That's called the power set of the Cartesian product. So this is the same thing for mathematicians. Either they say it's a subset of the Cartesian product, or they say it's an element of the power set. Sounds very powerful, of the power set of the Cartesian product. But you don't have to worry too much about this detail, right? So here's an example where we have a relation between strings and strings, right? So now if you look closer, you see you have universities on the left and cities on the right. And you have ETH Zurich with Zurich and Singapore. Yes, because there is actually an ETH center in Singapore. EPFL Lausanne, UCL London, UZH Zurich. And now you see again, why is there information? Because ETH Zurich is specifically associated with some, but not all of the cities. EPFL is specifically associated with Lausanne, UCL specifically London, UZH specifically Zurich. If you had the whole Cartesian product, you would have all of the possible euros absolutely everywhere. Again, that would be totally useless. There would be absolutely no information in there. There is only information because we have some, but not all of the pairs that are in here. That is actually data. Okay, now if I take these pairs, I remove these sets and take them out and put them one after the other, I get something like this, right? I'm just disentangling them like Mikado and putting them like this. This is a list of pairs, right? This is also how you can express a relation. You can also do it as a list of pairs. For example, here, you can have a list of pairs between strings. You can actually write them like this. In fact, that exists, that has a name. That's called a CSV file. Already saw a CSV file? Yeah. So a CSV file is basically a list of tuples, right? Comma-separated tuples, and you have new lines between the tuples. So you see, this goes in the direction of actual data. Then you can have so list of pairs. You can have also list of tuples. It's a more general kind of relation. Now it's a relation between three sets, not just two. So a relation between three sets is the list of three uppers, right? Of tuples of three values, right? So it's a subset of the Cartesian product of ABC. In other terms, it contains some of the tuples between ABC. Not all of them, because again, if we contain all of the possible tuples, we wouldn't have any information in there. There would be zero things interesting in there. But some of the tuples between A, B, and C gives you a ternary relation, a list of tuples, right? By the way, it can be a list, a set, a bag. I told you, right? You can have different flavors. And that can be generalized to any number of sets. We typically call these sets domains, right? So D1 all the way to Dn, right? And you have a set or a bag or a list of these tuples. Do you start seeing a relational table here? Who actually sees a relational table here? Starts feeling like it, right? This is a unary relation with just one, right? But technically it's just a subset of A, but still a special case that exists. Okay. I'll come back to that. That actually is almost a relational table. We are almost getting to a relational table here. Now there's another way to look at these relations. There's another way to look at them. It's in terms of predicates. A predicate is just a way of saying yes or no, does that tuple belong to your relation? If you take any possible tuple from the Cartesian product, it's a yes or a no. If it's a yes, it's in there. If it's a no, it's not in there. Mathematicians call it a predicate. It's again, function that associates either yes or no with every tuple. So all of those that you see here, they will be associated with yes, and all of the other tuples of the Cartesian product that are not in here, they would be associated with no, right? So yes, no, mathematicians call it true, false. So that function that I call PR here, that's a P for predicate associated with relation R, is returning true for red, yellow, orange, because it's here, it's in here, so that's true. Red, blue, orange, cannot see it anywhere here. It's not in there. It's in the Cartesian product, but it's not in that specific subset. It's not in there, so this is false. So it means that that gives us a second way of expressing a relation. We can also express a relation as a yes-no answer for every possible tuple, right? Okay. So here, for example, we could see this relation here as a predicate that takes a university and a city, and it says yes or no this pair of university and city is in there. So ETH Zurich, Zurich predicate would be true. ETH Zurich, I don't know, Berlin would be false. Okay? All right, so yeah, that's what I just said. ETH Zurich, Zurich is true. Oh, I said delete with Lausanne. Okay, so ETH Zurich, Lausanne, false. Okay, we have family there, but it's not the same ETH. Okay. All right, so we are kind of getting there. So that was the math, right? I inundated you and threw all of this math at you. A lot of you probably knew some or all of it. But now let's get back to our relational model. When I told you earlier, when I asked, okay, does it already start feeling like a relational table? This is why, for the few of you who might not have seen it yet, this is why. You see it now? So every cell, basically, that you see in your table, every value is basically one of these elements that you have on the right. Every row in your relational table gives you one tuple. So you can see the rows as tuples. This is why I said it's a synonym for row. You can call them tuples. This is really mathematically a tuple, as in a member of the Cartesian products. Okay, this is beautiful. This is why this is called the relational model. This is why it's called the relational databases, relational database management system, right? This is the reason. Relational, relation, mathematical relation, in the mathematical sense. Okay, so you see that there's math in there. So we basically define typically in many database textbooks, they will take the notion of a domain, which is a set, right? It's a domain of values, typically corresponding to what we want to be a column. So it's a set of all the values you accept. For example, the set of strings, the set of integers, the set of decimals, the set of booleans, the set of dates, the set of times, the set of sequences of bytes, if you want to store, I don't know, pictures or whatever in your tables. And so now I'm throwing this scary formula at you. You can define a relational table as a relation between the domains. In a relation, meaning the subset of the Cartesian products. Okay? So mathematically, we just write it like this. R is a subset of the Cartesian product of the domains. For whom does that make sense? Right? And that's really just this picture. That's the reason. Okay? So every row is a tuple. Every domain that's the set of values in a column. You start feeling domain integrity in there, perhaps. Yeah, we have a question.
Yes, so does every relational table have to have an index column that distinguishes each row from others? Or can there be rows in the relational table that are totally identical?
That are totally?
Identical. Same.
Identical.
Yeah.
So in this case, if you use this definition here, you will not have any duplicates because it's a set, right? R is defined as a subset, so that gives you the set semantics. It's a set of tuples. You cannot have duplicates of an entire row. What you can have, however, is that in a column, the same value might appear in multiple tuples. For example, you might have ETH Zurich Switzerland and EPFL Switzerland, right? So Switzerland is going to appear twice. Was it your question?
I think there is the first question. I think we can answer it later since we are not introduce the primary key things.
The primary key. Yes, this is what you meant, the primary key. Yeah. This is something we'll see in a couple of weeks in database design theory. The answer, at least the theoretical answer is, if you are in the set semantic, the answer is yes. You will always be able to find a primary key. However, the primary key may not be a single column. Primary key might be made of multiple columns. For example, cars, for example, license plates on cars. You might have the content plus the number. That would be two columns together, right? So the answer is yes, but it might be more than one column. But if you have the back semantics, then no. If you have the back semantics and you have duplicates, then that might actually not work. Okay. Yep, great. Okay. Going to close the chat window. Okay. So that is our first attempt. In fact, it's the textbook attempt to define a relational table as a relation between domains. So then that's an example. That's the one we had. This is a relational table because it's a relation between strings and strings. Right. That would be just the visual representations. That would be the CSV file, and that's when you import it in Excel, right? Okay, so this is a relation. It's a set of pairs. So that's basically what one of you remarked, that you can have set of pairs. That's just a particular case, right? So we have a first column and a second column. Okay. But you might start noticing something here. The columns do not have names. Notice that? 1, 2, there's no names in there. So this is where we start hitting the limits of that definition. All right, so now if we go further, what is an element in a relational table? That's called a record. A record is the same thing as a tuple, a row, and so on. So it's just an element of the relation. Any element of the relation, a tuple, is called a record. Record is really the database term for the tuples and the rows, okay? Records. This is a record, right? It's a tuple, ETH Zurich Singapore, a pair in that case, and that's what we call a record in database terms. We call it T typically because T like tuples. So in textbooks, when you start doing proofs of theorems and so on, you often call them T, U, and so on. Okay. All right, and then you can index. You can use an index, right? There's the first one, the second one. In fact, in mathematics, this is what you do when you have Cartesian products. You use the subscript 1 for the first value, 2 for the second value. So if you have T, then T1 is ETH Zurich, and T2 is Singapore. For whom does that make sense? Okay. That was, in fact, the first idea, and the reason why it's actually called a relational and relational table. But there's a couple of problems with that. There's a couple of problems because it doesn't actually fulfill everything that we wanted, right? The first problem is that the order of the attributes actually matters, because if you have a Cartesian product, there is actually an order. For example, if you have the plane in analytical coordinates, you have an x-axis and a y-axis. The first coordinate is the x-axis, the second one is the y-axis. There is an order between the two. But I told you in the beginning, we do not want there to be an order between the attributes. We would like to swap the attributes and it's the same. What makes it worse is that these are numbers and we wanted to have names in there, right? And this is something that is not captured by the Cartesian product. That doesn't give you that. So we are not quite there yet. And even though in textbooks, this is how often it's made, we basically give the very heavy and precise mathematical definition as a mathematical relation. And then we wave the hands and saying, yes, 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 but there's names to the columns and we can swap and so on, but then that feels less mathematical, right? So this is a bit unsatisfying, basically, this thing. So I have another definition that I'm going to give to you that is actually a bit simpler, and it's even a definition that is forward compatible with big data, right? And that would give us relational tables where the columns actually have names, right? Called headers also in some situation. Okay, so if you read a database textbook, this is what you will find. They will tell you a relational table, it has a schema. What we call the schema is basically the name of the attributes plus the domains. And then we have the actual values that are in the Cartesian product. But you see the association with the attribute names and the domains that totally outside of the definition of the Cartesian products, right? So it feels glued together, basically, this thing, okay? All right, so that's the textbook definition. You have domains, attributes, domains, and you take a relation between the domains, a subset of the Cartesian product of the domains, that gives you the table. Extension is basically the name we give to the actual set of tuples, the actual data if you forget about the headers. Now, if you do use that definition from the textbooks, you will notice that it gives you domain integrity and relational integrity for free. Who sees that? Right? Gives you domain integrity because by definition, you have the Cartesian product of the domains. So that forces the values to belong to the domains in every column, right? The first column will all have it in the domain of the first attributes. The second column, that's all in the domain of the second one. So it's by definition, you have domain integrity. Relational integrity is also by definition because it's a subset of the Cartesian product. So a tuple is always in the same Cartesian product. It will all have always the same number of attributes, right? Same number of of values. So by definition, you also have relational integrity. But you might not have atomic integrity. Why? Because the domains might contain non-atomic stuff. You can have a domain that contains tables or lists or dictionaries and so on, because we can have any domains technically. Okay. So again, domain integrity by definition, relational integrity by definition, atomic integrity if we additionally say the domains must have atomic values only, right? Strings, integers, dates, but not tables and so on. At least not in the beautiful world of SQL. Okay. So that was the, yes, there's a question.
I just wondering how in the previous example, we had two experience of ETH Zurich being that a domain is a set of values.
So the fact that it appears twice, you mean?
Yes, he think is a set of values, so there is can't be twice.
Yes, it is true. Let me go back to a slide earlier. Here. I said a relational table is a relation, right? A domain is still a set of value. This is the domain A, strings. This is the domain B. But do you remember that in a relation, we allow for a value here to be in multiple pairs, to be associated with multiple values. This is why, even though this is a set, you might still have several rows coming from the same value in here. That is the reason why, in that case, for example, that would appear twice, and this one would appear in 3 different brackets. Does it make sense? It's all because this is a relation. Yeah. All right. Never be sorry about asking a question. This is a university, we are learning, you can ask all the questions you want about the material. Okay? All right, so let's go. Yes, that's the first attempt. That's the scary one, the textbook. And now we get to second attempt. Okay. So that was the first definition. What is there to learn in there? What insight do we have? Well, we learned why a relational table is called relational. It's called relational because that can be defined as a mathematical relation. Okay. Let's attempt second attempt. Let me go back to one slide before we do that. That will actually explain that second attempt because we actually saw it somewhere. This one. So that one corresponds to the first attempt, right? We have a tuple that belongs to a Cartesian product. The second attempt, this is it. That is the way we go with the second attempt. In the second attempt, what we'll do, instead of taking tuples, what we'll do is we'll take maps from attributes to values. If you get that, then this is the second attempt. This is what we'll do, right? Okay, so take a snapshot of this in your brains. This is how we are going to approach it in our second attempt. We map attributes, some attributes to values. Okay. Now I'm going back. It's a lot of slides. Okay. So in the second attempt, we start with attributes. So we have a set of attributes. An attribute, what is an attribute? It's just a string. That's just what you put in the header row, right? So it's a string. An attribute is a string. Who heard about monoids? Okay, I'm not going to scare you with that. If there had been mathematicians, I could have told you this is a monoid with concatenation. You can sound smart in front of your friends with that. But let's forget about monoids. Yeah, just a curiosity. Okay, so attributes are strings. These are attributes. Foo is an attribute. You know where foo, in computer science, maybe if you didn't attend computer science courses before, when we don't know what we put in a string, we use foo and bar. Do you know where that comes from? It comes from the word furchtbar, because they heard, at some point, somebody heard German-speaking people like furchtbar, and furchtbar became foobar. And now we put foo and bar everywhere in all computer science lectures. We do it a lot at ETH. You will see this is basically something that we do. So foo, this is why it's called foo, comes from this. Okay. So full name, first name, birth date, product ID, account ID, ETH Zurich, EPFL. So any string can be an attribute. But now, of course, they don't all make sense, right? An attribute, basically those that make sense here would be name, first name, birth date, product ID, account ID. These make sense as colon name, right? ETH Zurich, EPFL, no, that would be strange. These are not colon names. These are actual values that you put in there. But when you define it, you just say, okay, an attribute is a string. You can call it whatever you want, right? And then as a human, of course, you want to take those that actually make sense as headers. All right. So these are examples. And now we are going to define the records of our relational table, but differently. We are not going to define the records as tupples, as we did in the first attempt. No. This time, we are going to define a record as a map, according to the snapshot I told you to take earlier. So a record is a map. It's a map from attributes to values. Okay? It's a member of this set of maps from strings to values. Okay? V, at that point, can have atomic or non-atomic values, I don't care, right? It's just whatever values you want. This is an example of map, and thus that's a record. So what we have here, it's a map. I used the mathematical way of putting it. I could also have used the pictures with arrows and so on, but I just decided to do it more formally. So it's a mathematical definition of a map, a partial function, that associates 4 attributes. There's many attributes, but 4 of them, last, first, physics here, 4 of them get associated with a value, right? Last, it's associated with Einstein, first with Albert, physicist with True, here with 1905. That is a map, right? It's a map from strings to values. It's a partial function, a map, because it doesn't map the other attributes, right? There's the attribute, for example, a country, it's not in there, right? There's the attribute a product ID, it's not in there, right? So this is a map. Some of the attributes get mapped to a value, 4 of them. Oh, I have the visual, in fact. So this is basically the visual I told you to take a snapshot of, right? So now this is also a map, but just drawn visually. It associates name with ETH Zurich, city with Zurich, department with DMAT. That is a record with 3 columns, right? Do you visualize it in your head as a small table with 1 row, right? Name, city, department, these are the headers of the columns, and ETH Zurich, DMAT Zurich, that's the values in the cell. Okay, so this is really the same thing. This is just the visual when you draw it. And this is what the mathematicians do when they actually list the associations in the map. Now, computer scientists never do that. You will not find that. I'm pretty sure you will not even find that in a database textbook. What computer scientists do, however, is this. But you see, it's the same thing, right? This is exactly the same thing here. It's just expressed differently. Do you know how that is called? This syntax? Whoever heard of JSON? This is JSON. It means JavaScript object notation. Very popular on the web. If you program with JavaScript, or if you use some APIs with databases, this is called JSON. We are not going to really look at JSON in this lecture. We do it in Big Data for Engineers. But just to make a connection, if you know what JSON is, a JSON object is a record. A JSON object is a map, right? It's really all the same thing. Okay. And that here is now the relational table E way of putting it. It's exactly 3 times the same thing, right? As mathematical records, as JSON, as now a table with 1 row. Okay, so you see on the first one is the headers, doesn't count as a row, it's just the headers. Then we have the values there. Do you see now the beauty of it? Do you see we've solved the problem of the order of the attributes? Because in a map, look at this. There is no order in the rows here. It's just a spaghetti ball here, right? There is no order between name, city, departments. So it means that here, there is also no order between the columns. You can change them and swap last and first or last and physicists and so on. Now, the math captures that the order of the columns is irrelevant. So we've solved that problem by using the definition of a record as a map. So that's great. We achieved what we wanted, right? This is another example. universities, ETH, CT Zurich. Okay, so now we continue on our reasoning. I can consider sets of attributes, right? For example, this is a set of 4 attributes. Since we said that attributes are strings, then a set of attributes is just a subset of S, right? So it's a subset of the set of all strings. It's a set of strings. Okay. Now, how do we put that in relation with the maps? Well, there's the notion of the support of a map. The support of a map is basically the set of the attributes that get a value. So the support of the map that you see at the bottom here, Albert Einstein, basically, this here is the support, right? This is why we get that. If you look at here, this here is the support. This is the support. It's a subset of S. S is an enormous set. These 4 together, the set of these 4, is the support of that map. Okay, for whom does that make sense? Right. So the support of a map, the support of a record, is the set of the attributes that actually do get a value in that record. Now, probably start seeing where this is getting at. If we consider now a collection, it's a very generic term for data sets. We can say, okay, a collection is a set of maps. You give me maps, plenty of maps, that together is a collection, it's a data set. Now, the problem is that if you just say that, if all you say is a record is a map and a table is a collection of records, the problem is that you also accept that this is also a set of maps. Who agrees this is a set of maps? That's 3 maps, right? But what's the problem here? They don't have the same support, right? The support of the first one is last first physicist here. The support of the second one is last first physicist. The support of the last one is last first year theory. They don't have the same support. So generally, we call it a collection if we don't care if they have the same support or not. It's a collection. This is a collection. But if we want to also ensure what we now know is called relational integrity, we additionally say we want these maps to also have the same support. If they do have the same support, we can glue them together in this way, right? In this way, yes. Okay. Now, that's relational integrity. Now, what about atomic integrity? Well, atomic integrity just is about how we define a value. If we say the values must be atomic, V is only atomic values, then we've also checked the box of atomic integrity, right? It's really just a matter of what values we allow. So if we say we don't have tables or dictionaries or list of whatever that has structure, we don't allow that in V, only strings, integers, dates, and so on, then we have atomic integrity. What about domain integrity? Well, that is also an additional constraint. Then we just ask that in every one of the maps, all the values associated with last must be in some identical domain. All of these must be in some domain. Here, strings, all of them must be in some domain, Boolean, and so on. So that's also a third constraint that we add to the mix, right? So you see, if I do that, then I can do this. This is the yellow line. We'll see it all the time in the coming weeks. This yellow line that has the types of the columns. We'll also see how we do it with SQL to define them. Again, I insist that's not a row. That's just the names of the domains. Okay, then we have domain integrity. So now we can define it mathematically. Don't be scared, it's a lot of text, but if you look at the picture, it's much easier. It's really the idea that we add domains in there, and we require that if we take an attribute, A, and if we take a record, I still call it T like tuple, but this is more because we use them interchangeably, then T.A, which is basically how we call the value in here, T.A, belongs to the domain D. In other words, everything that is in there must belong to that domain. Everything that is in there must belong to that domain. Everything that is in there belongs to that domain. Then we have domain integrity. So what you learn here is that none of the integrity constraints are actually captured by saying that it's a set of maps. So all 3 must be explicitly added on top, right? In addition to saying it's a set of maps, we need to additionally say it has to have atomic integrity, it has to have domain integrity, it has to have relational integrity. All right, so relational integrity means all the maps have the same support. Domain integrity means in the same column, it's always the same the same belongs to the same domain. So this has domain integrity, right? Here's all a string. And here it doesn't, right? It's an integer, but that's not an integer here. That's a letter, right? So that breaks domain integrity in that case. Okay. So you see, now we have again these three rules that I told you at the beginning, but with the second attempt as defining a table as a set of maps, we need to additionally require these three. Why is that a good thing? Because then in big data for engineers, all I will need to tell you in the first week is now we take what we did here, we just drop this, drop this, drop this, and we allow everything. So it will be really simple to go to big data doing it like this. But in this lecture, we do require these three things. We do want the maps to have the same support. We do want the values in the same column to belong to the same domain. And we do want the values to all be atomic. Okay. So a relational table is a set of maps collection that additionally fulfills the three, right? So now it's easy. That's a collection. It's a set of maps. If we add the three, then that's a relational table. In the map semantics, that's very easy. A collection is a bag of maps. And if we add the three constraints, we get a relational table with the map semantics. What about the list semantics? Super easy. A collection is a list of maps. And a relational table is the same thing with the three criteria. All I really did here, I just said map or list instead of sets. That's all I did. So you see how easy it gets. That you cannot do with the first definition as a relation, because a relation only gives you the set semantics. So you see the power of that second definition is that you get the bag semantics and the list semantics just by calling it a bag and a list instead of a set of maps. Who understands this? Right? Very good. Okay. Noon is approaching, so let's just go here. I'm pretty sure it's good. Yeah, it always does that because I waited for too long. So I just want to know every time. That's the way you can tell me slow down, or accelerate. It's not fast enough. I'm bored. This is your opportunity to basically let me know, right? So every time it gives me an impression, like, do you get it? Is it too easy? Is it too difficult? And then I adapt my rhythm. I accelerate or slow down. I know that people accelerate me when they listen on YouTube, right? You can turn this plus 25% of, and then you hear me speaking like that very fast, very fast. Okay. So my goal generally is that I would like most people to be above 80. That's my goal. If everybody is above 80, it's fine if it's not 100%. You can read the textbook. By the way, I put it on the Moodle, the chapter of the textbook. So it's fine if you're not at 100%. If I start seeing that a lot of people are below 80 or even below 50%, then I can take the time, Q&A, answer questions, and so on, to make sure. So here it seems to be a good balance. Don't hesitate to interact with each other. You can ask questions on the chat. Everybody is there. You can ask questions to the TAs, to me. So we are here to help. This week is theory. Don't worry. Next week is practice, right? So we really alternate between the two. Next week will really be much easier than looking at just math. Okay. Thank you very much, everybody. Enjoy the exercise session, right? Let the TA team know if you don't manage to make the Docker work. I'll see you next week at 10 a.m. for the end of this and then a bit of SQL. Thank you.